In this video, we're going to look at using derivatives as rates of change. And the classic example that a lot of calculus classes like to use for using derivatives as rates of change is particle motion, which is the example that we have given to us. It tells us to suppose a particle moves along a coordinate line in such a way that its position is described by the given function, which we have a cubic here, for the interval t greater than 0, but also less than 2. So that's the window we're dealing with. And the first question asks us, well, what's the particle's velocity as a function of time? In class, we described the relationship between position, which is s of t, velocity, and acceleration. I don't need to put equals, they're not equal to each other. So we have s of t, velocity of time, and acceleration as a function of time. The relationship between them is that velocity is the derivative of position, and acceleration is the derivative of velocity. Okay? So what we're doing in this case is we're going to go ahead and erase this because we've kind of recovered that now. We have that the position function, when we take its derivative, we get the velocity function. Okay? So what's the derivative of our original position function? Well, here what I see is we can use the power rule on each of these terms individually and then put them back together in their original function form. So if we use the power rule on 3t cubed, we get 9t squared. Okay, and then we have minus 9 halves times 2, so we get 2 times 9 halves times t to the 1. But when we multiply 2 times 9 halves, the 2's will cancel out because it's 2 divided by 2 that evaluates to 1. So what our velocity function actually becomes is 9t squared minus 9t. And again, we're just going to reiterate that this interval that we're dealing with is all t's greater than 0, but still less than 2. So this is our derivative function. This is velocity of time, which is also, as we said, the derivative of the position function. So we've taken care of the first question. The next question that we're asked is we're asked to determine, right here, determine open intervals where particle is moving left and moving right. They're going to be two different situations that we run into. Moving left is one situation and moving right is the other situation. So we took this derivative just for kind of reasons we're not sure of yet. We found it, but then we're asking ourselves, well, how does this play into this next question? Well, what we have is in the case where the particle is moving left, how that actually works is we're going to find that the velocity function is negative, and when we move right, that's going to be the case where the velocity function is positive. So in order to kind of explain that a little bit more clearly, let's take a step back to when we started graphing functions and their derivatives and kind of think about what this stuff means. We know that velocity is the derivative of position, right? Well, what happens when the derivative of a function is negative? Well, it means that the original function has decreasing values in it, and the opposite is said for when the derivative is positive. That function has increasing values. So what this means in the context of our problem is that in our question, we're told that this particle moves in a coordinate line, and usually with these kinds of questions we get it's a straight line motion or something like that. So in these cases, I'm going to draw a little visual that helps me to understand what these questions are asking and kind of put them in context for you guys. So we have, this is position 0, this is 2, just for sake of what we're doing. And what I'm going to kind of do is roughly sketch just a situation. It's not really relevant to this question, but just kind of in general about what we're doing. So suppose on this y-axis, what we're going to have a particle doing is shuffling back and forth on this axis, just going up the axis and down the axis. But what we're going to have it doing is to where the particle, let's say it starts here at 0, 0, we want the particle to face this way for this example. Because what's going to happen is as it moves up the y-axis, what that particle is doing in its perspective is moving to the right. And when that happens, the motion is graphed with increasing values. And say right here it changes direction and goes back left all the way down here. What happens there is the values of our position function go back to decreasing all the way till we get here, and say it changes motion again, to where it goes here, and that's the end of our interval, so it goes back up positive. So we can kind of see how that relationship works out with particle motion moving left and right and how it plays into the derivative, okay? When the particle's moving right, we have increasing values on our position function. When it's moving left, we have decreasing values in our position function. So what I'm going to do is I'm going to take care of clearing this off because we need the workspace, but that's what I like to keep in mind with these problems as I'm working them, is just to think about, okay, how does this look as the particle is moving? But now that we've set the stage for this, what we're going to be doing is figuring out where our velocity function's negative and where our velocity function's positive. But in order to start that process, we got to find out where it's zero. Because where our velocity function is zero, we got to keep in mind velocity is the derivative of the position. So where the derivative is zero, that means that there's a relative extrema happening at that point, which translates to either a minimum or maximum, kind of what happening there. And when the derivative, in this case velocity, is zero, the particle's not moving at all. In fact, it's changing direction. So when we find where velocity is zero, we can use that as a point to investigate other sides of our interval with respect to that point to figure out if our derivative is positive or negative to know if it's moving left or right in a whole sense. So before we get too farther into this whole process, let's figure out where 9t squared minus 9t equals 0. Okay, so in this case, let's just solve for t. So here what we're going to do is we're going to add 9t to both sides just to kind of split the difference on them right here. So we have 9t squared equals 9t, and if we divide 9 away, the relationship that we're left with is t squared equals t. So our next step could be, and I'm going to kind of write this in dashed lines because it's not the best way to solve this problem, could be just to divide a t here, because t squared is t times t. So if we divide by a t here, we're just reducing the power here, and this becomes t equals 1. This is perfectly fine and dandy for this case, but I want to evaluate about why this is true here. When we look at this relationship of t squared equals t, there are two numbers that actually satisfy this expression, that its squared value is the same as its original value, and that's 0 and 1. 1 squared is 1, 0 squared is 0, right? So the only reason why we don't count 0 as a potential value for this is it's not in our interval that we have in question. We have this interval here for a reason, and so because of that, we exclude this value of t equals 0 to where we're only worried about t equals 1. So again, what happens at t equals 1? At t equals 1, our velocity function equals 0, and what this means is our position function, s of t, is changing direction, going from increasing to decreasing. So we're going to use this to evaluate on which side of t equals 1 is our derivative positive and on which side is it negative. So in order to do this analysis of where the derivative is positive and negative, what we're going to end up doing is using this t equals 1 as almost a split of our interval of 0 to 2. And what I mean by that is we're going to pick a value to the left of 1 but still greater than 0, and a value to the right of 1 but still less than 2. So what we're going to do is we're going to pick a t in the interval 0 to 1 and evaluate v of t. And we're also going to do the same thing for v of t. We're going to pick a t in, but in this time the interval is going to be 1 to 2 and evaluate v of t. Okay, so in this case what I like to do is kind of pick the value that'll give me the path of least resistance, and in this case what I think that'll be is 1/2 because it's represented as 1 over 2, and it's really just kind of easy to work with. We're familiar with dealing with 1/2 as opposed to something like 7/9 or 1/11. In the similar way, I'm going to pick t equals 3 over 2. Okay, so at v of 1/2, we said that our velocity function is represented by 9 times t, and in this case is 1/2 minus 9 times 1/2. Well, how does this evaluate? We have 9 times 1/2 squared gives us 1/4 minus 9 over 2. So here we get 9/4 minus 9 over 2. And what this is by using a least common denominator here, we can simplify this. We get 9/4 minus 18 over 4. So this becomes negative 9/4. This sign right here is what we're really concerned with. Because when, like we said, when our velocity function evaluates to be negative, that's when our particle is moving left. So in 0 to 1, velocity is negative, and this implies particle moves left. So knowing this, we know that at least one of these intervals has a particle moving left. And I said earlier, kind of preemptively, that when our derivative is 0, we could have a change of direction. It may not always be the case. We could have local extrema that give us a maximum or a minimum, but the values of our derivative don't change, like if it stays negative on one side and the other side. So it could be that it's kind of almost like a disguised maximum. It kind of is there to trick you. So what we're going to do is not just readily assume that from 1 to 2 the particle is moving right. We're actually going to check it. Okay, so we have v of 3 halves equals 9 times 3 halves squared minus 9 times 3 halves. Okay, doing this algebra in our head, really, we get 9 times 9 over 4 minus 27 over 2. This becomes 81 over 4 minus 27 over 2. Then if we find an LCD, we get 81 over 4 minus 54 over 4, which gives us 27 over 4. Luckily, in this case, we know that our derivative, or velocity here, is positive. So in 1 to 2, velocity is positive. So that implies that the particle moves to the right. Okay, so we figured out what intervals the particle moves to the left and the right. And so now what we're going to do is we're going to look at the next step of our question here. And what that is we want to find the particle's acceleration as a function of time. So find particle's acceleration. As a function of time. Try to abbreviate here and just do a little shorthand as a function of time. So similarly to how we said that s prime of t gives us velocity of time, the derivative of our velocity gives us acceleration, right? So technically what this is the second derivative of the position function. But in order to find acceleration, we're just going to take the derivative of our velocity function, and we said that our velocity function was 9t squared minus 9t. So if acceleration is the derivative of this, we're going to use the power rule again to give us 18t minus 9. So our acceleration function is given to us right here. This is our particle's acceleration as a function of time. So similarly to how we were asked, okay, we're going to determine intervals where something's happening in respect to velocity, we're asked something similar, but it's got interesting stipulations within the problem itself. So here what we're doing is we're determining open intervals where particle is speeding up and slowing down. I have speeding up and slowing down. Before I get into the inner workings of what this problem is going to look like behind the scenes, let's do the similar approach that we took last problem of figuring out where acceleration of time equals 0. Okay, and the reason for that is we're still going to follow the same process of evaluating values of our acceleration function on either side of the spot where this function becomes 0. So the t value that makes it 0, we're going to pick values and evaluate them to figure out whether our acceleration function is positive or negative, because that will play into determining whether or not our particle is speeding up or slowing down. So our acceleration function equals 0. This becomes 18t equals 9. If we divide by 18, we get t equals a half. So at t equals a half, acceleration is 0. Okay? So let's go back and talk about what it means for a particle to speed up or slow down. In order for a particle to speed up or slow down, we can't use the simplistic approach we did with velocity of just figuring out where it's positive and negative and having that be our answer. we need to also take the direction of its movement into account. And that's our results from our analysis of velocity, right? Because when we found that the velocity function was positive, that particle was moving to the right in that interval. And when our velocity function was negative, that's where our particle was moving to the left. So what we need to do for figuring out speeding up and slowing down is we need to figure out first, now that we've done all that work with velocity, we still need to figure out where acceleration is positive and where it's negative in our case. So we know that t equals 1/2 is kind of that change in direction moment. It changes from positive to negative or negative to positive at 1/2. So let's go ahead and evaluate a quick couple of values, one on the left of 1/2 and one on the right of 1/2, to figure out on which interval it's positive and negative. So t in 0 to 1/2, because that's our interval, we go from 0 to 1/2, because our big interval is still 0 to 2, so we're chomping that down to 0 to 1/2. So a t in 0 to 1/2, let's pick t equals, say, a fourth. And for a t in 1/2 to 2, let's pick t equals 1. Again, you want to pick something that gives you the least amount of resistance. That's why I picked 1. It's a nice, easy number to deal with. So, not at, my fault. So if we have a of 1/4, that's going to translate to 18 times a fourth minus 9. And this is 18 over 4 minus 9, or 18 over 4 minus 36 over 4, which is negative 18 over 4. This negative sign, what does that tell us? That in 0 to 1/2, acceleration is negative. Okay, so let's evaluate now a of 1, because that's our value that we picked for the other interval that we've broken this into. So we have 18 times 1 minus 9. We get 18 minus 9, or 9. So in this case, 1/2 to 2, acceleration is positive. So now that we know where acceleration is negative and where acceleration is positive, and we know where velocity is positive and velocity is negative, we need to take all of this into account to address what constitutes a particle speeding up and slowing down. So in order for something to speed up, our particle needs to move to the right with a positive acceleration or move to the left with negative acceleration. So what that means is that if our particle, say he's right here, he decides to move to the right, if in order for him to speed up, what he needs is an acceleration that's also moving to the right with him. It's giving him a faster boost and he's speeding up as he goes. It's kind of like pressing on the gas pedal. And in the same notion, if he's moving to the left like this, because we're still kind of thinking that he's facing this way, up and down that coordinate axis like I detailed earlier. So if he's moving to the left, he needs an acceleration that's moving with him, meaning that acceleration's got to be negative. So what this means is for our particle to speed up, sines of v of t and a of t will match. And it's the exact opposite for slowing down. If he's moving to the right and has some type of acceleration force working against him in this way, what's going to happen is he's slowing down. And it's the same thing if he's moving left and the acceleration's moving to the right like this, it's going to cause him to slow down. Whatever velocity he's got here moving to the left, it's going to get acted on by this acceleration going the other way, so it's going to slow him down. So in order for a particle to slow down, the signs of v of t and a of t will be the opposite. So that's the relationship that we're looking for here. If our signs of v of t and a of t match, he'll be speeding up. If the signs of our velocity and acceleration do not match, the particle will be slowing down. So let's move over here and depict what's happening in our velocity and acceleration functions. So when we talked about velocity of time, let's make a little, just kind of like a little number line here, from 0 to 2. We knew that there was a break when t equals 1. And on either side of 1, we knew that from 0 to 1, velocity was negative, and from 1 to 2, velocity was positive. Let's take the same, it's not at again, I keep drawing ats, I'm sorry. When we have a of t, we saw that same big interval 0 to 2, but we had a different change in sign point at 1/2. And we said that in 0 to 1/2, our acceleration was negative, and from 1/2 to 2 our acceleration was positive. So now let's kind of try to bring these points of interest onto the respective other timelines here and see what we can come up with. So when we're in the intervals 0 to 1/2 in acceleration and velocity, our signs match. We see that because 0 to 1/2 acceleration is always negative, and in 0 to 1/2, which is like a kind of like a subinterval of 0 to 1, our velocity is negative here. So from 0 to 1/2, our particle speeds up. Okay, but what about 1/2 to 1, right? Because we have, in the case of acceleration, we know that from 1/2 to 2, this is positive. But in velocity, 1/2 to 1 is still negative. So in the case of 1/2 to 1, the signs are opposites. And what happens when the signs of velocity and acceleration are opposites? It slows down. The particle slows down. So we have from 1/2 to 1, our particle slows down. Okay, we have one more interval to deal with. And luckily for us, from 1 to 2, in both cases, velocity and acceleration, the signs match. So we can add it into our collection of intervals up here to say that from the interval 1 to 2 and the interval 0 to 1/2, our particle speeds up. And in the case 1/2 to 1, our particle slows down because the signs are opposites.